All right, I already defined Doppler effect. Doppler effect. What's Doppler effect? The apparent change in frequency of the source of a sound due to the relative motion of the source and observer. So there are two things. One is source, which is producing the sound, and the other is the observer, which is the receiving end. So the observer hears a totally different frequency when there is an apparent movement. Okay, when there is a movement. So when there is a relative movement, there is a change in frequency, and that change of frequency can be higher or lower, and that depends on multiple factors. Now, so we'll look into that step by step. So let's talk about this source producing a certain frequency. Okay, I already told you how the Doppler effect is in terms of the wave forms. The waves get compressed on one side and stretched out on the other side. So when the waves get compressed, the wavelength is getting affected, right? And that is what changes the frequency. So if this is sending out certain frequency, if the frequency that is sent out is, if the source sends out a frequency f, so here are the waves that are going out. Now I'm just not drawing circular waves now, I'm drawing straight waves. So these are the waves that are going forward. What's the distance from one wave to the other? The lambda wavelength. So he's sending out f waves in 1 second. That's why it's called frequency, right? What's frequency's definition? Number of waves sent out per second. So if this is 100 hertz, it means 100 waves are sent out per second. So when I say f is the frequency, there are f waves in 1 second. Now, the wave is moving at a speed which is speed of sound. That's the speed of sound. What's speed of sound definition? It's a distance moved by the waves in 1 second. So now let's look at the 1 second period of time. In 1 second, how far did the first wave move? V meters. Is that right? So the distance from here to here is V meters in 1 second. So I'm looking at 1 second. How many meters moved by the first wave? V meters. And how many waves are from here to here? No, forget about the numbers. I just gave a number as an example. F waves. F is a frequency, right? That means in 1 second, how many waves are generated? F waves. And F waves are accommodated in this distance of V. That makes sense? So in 1 second, the first wave has advanced till here, of V meters. And in that 1 second period of time, there are F waves generated. That means from this point to this point, you must be having F number of waves. Accommodating what distance? What? V meters. So what is the distance between two waves? It will be this distance divided by F. Isn't that so? Isn't this? What is the wavelength? Wavelength is V divided by F. V is the total distance, and there are F waves in that space. Make sense or not? Okay. There are F waves taking up a distance of V meters. Therefore, the distance of each wave is simply V over F. That is the wavelength equation. Now let's look at an observer. The observer is hearing the waves with a frequency, with a new frequency. So I'm putting F prime as the new frequency that is he is hearing. Now what is the frequency that he is hearing depends on how fast the waves are approaching him, and it also depends on how much is the wavelength. Is the speed of the wave approaching him the same or different? Same. Is the wavelength of the waves approaching him same or different? Same. So therefore, what do you understand now? The frequency that is sent out is V over lambda. The frequency that is heard is V over lambda. And so he hears the same pitch. You get it? So if the source is stationary, not moving, if the observer is stationary, not moving, that means you will hear exactly the same frequency as is generated. Okay? So the frequency that you hear right now, I'm not moving. This is 384 hertz. So when I hit 384 hertz, this is generating 384 waves in 1 second, and it's supposed to accommodate a distance of 340 meters in that distance, right? So 340 meters, how many waves? 384 waves. So what's the wavelength? It is 340 divided by 384. That's a wavelength. So 384 is the hertz. Now you are the observer. At what speed are the waves reaching you? V, same 340. And what's the number of waves? What's the wavelength? It's the same wavelength that is generated. And therefore you hear exactly 384, no difference. You hear exactly 384 hertz because that's what's generated. So what is generated is this. What is being heard is this. Now we're going to see the consequences of movement. If the source is going to start from here, it is generating waves, it is creating waves from here, but it's not going to stay still, instead starts moving this way with a speed which is known as the source speed. Alright? So the source was here in the beginning. When the first wave was sent out, where's the source? Right there. And where will that first wave go in 1 second? Where will that first wave be in 1 second? V meters. The first one is going to be in 1 second. The first wave which was sent out from here is going to be there. But this time the source is not staying still. It is moving. Which way? That way. So the source is moving with a speed which is Vs. The source is moving with a speed which is Vs in that direction. And what do you mean by Vs? Vs means he travels Vs meters in 1 second. So the first wave in 1 second has gone till here. The source itself in 1 second would have gone till here. What is this distance? Make sense? The source also is moving. And so in 1 second, the source moves from here to here. Traveled already Vs meters. How many waves does this source generate in that 1 second? F waves. That's the same thing. So that means what? He started generating the waves when he was here, and he finished with the F waves when he finished here. Where are all those waves now? They're all here. They're all here. All the waves that was generated, they are here, right in front of him. Do you think the wavelength is affected? Yes? Why is the wavelength affected? Because it's getting compressed. How can you find the wavelength? What is this distance? What is that distance?
V minus Vs.
V minus Vs. And how many waves are in that space? F waves, right? There are F waves, look. There are F waves in that region. There are F waves in this region. There are F waves in that region. There are F waves from here to here in a shorter region. So what is lambda prime? How much is lambda prime? What's the lambda prime? How do you find it? How do you find lambda here? V is the total distance from here to here over the number of waves. Now do the same thing. What's the total distance from here to here? And what is the number of waves? So lambda prime is V minus Vs over F. Is that clear? Over here it's just V over F, but now here is V minus Vs over F. Now let's look at the observer. The observer is going to hear a different frequency, probably. Now that depends on two things. One is speed. How fast are these waves reaching him? Faster or slower or the same? Same. This is going at the same speed. In 1 second it traveled from here to here. So it's moving at the same speed. Look, in 1 second the wave goes here. In 1 second the first one goes here. It is just speed of sound. So speed is not affected. What is affected? What is affected? The wavelength. So the wavelength is lambda prime. And how much is lambda prime? Put that there. So F prime is going to be V over V minus Vs over F. And that brings us our equation F prime is equal to, when you're dividing it by a fraction, you multiply it, right? So you get V over V minus Vs times F. So that is your equation for frequency. So the frequency heard by the observer is going to be higher or lower by the look at this equation. Higher because it's subtracted here. If the source was not moving at all, look at that. If the source was not moving at all, just remove this whole thing. So you'll have just V over V, which is 1 times F. If the source is not moving, then this Vs won't be there at all. But if the source is moving, then you are having a smaller number in the denominator, which makes the whole thing bigger. So F prime will be higher than F. So F prime will be greater than F. Yes?
Is there supposed to be a prime signal on that first F up there? Under like...
This one?
Yeah.
Yeah, I just put it there because that's a new frequency, but now you see that that is the same thing as this. So this is F.
Okay.
So the frequency as heard by the observer is F. That's what you understood from here. But now you see that the frequency that is heard by the observer is not F. It is that fraction of F, which is going to be bigger now. That is why it's greater. So here F prime is F, and here F prime is greater than F. Make sense? Okay? Now I'm going to discuss what happens if this guy is going to go backward. So the source is here. He's producing energy which is going everywhere, right? How far has the first wave gone in 1 second? Same place. The first wave has gone there. What's the distance from here to here? V meters. But now the source is going backward. So in 1 second, where is he? He's here. In 1 second, he's gone backward. Vs meters backward. So the last wave he's generating from here. And the first wave he generated from here. So where is the first wave? Right there. Where's the last wave? It's here. And how many waves are supposed to be there between these two locations? F. So you're going to have... So what's the consequence? What's the consequence? There are F waves from here to here, and the total distance from here to here is how much? V plus Vs. Get it? So what is the new lambda? The new lambda is V plus Vs over F. because he's going away, he is increasing the wavelength, not decreasing the wavelength, he is increasing the wavelength. So now let's find out the observer. The observer is going to hear a frequency f prime, which depends on the speed, which is not affected. Speed is the same thing. And lambda is affected. And the new lambda is this. So it's going to be V over V plus Vs over F. So the equation becomes F prime is V over V plus Vs times F. So F prime is going to be smaller than F. Why smaller? Because the denominator is bigger. You get it? The denominator has gone up, therefore the frequency has to go down. Any questions on this? So I've shown mathematically how the frequency is really affected when the source is going to go towards the observer and when he's going to go away from the observer. So this is when the source moves away from the observer. You can write it down here. Source moves away. Away from observer. Then the frequency as heard by the observer is going to be smaller. Consequence is because of the wavelength getting bigger. So you understand these two situations, what happens when the source goes towards, what happens when the source goes away, right? Now we're going to put the source in the same place. Now we're going to make the observer move. All right. No questions here? Oh, okay. I want that picture. All right, now the source is going to stay still, producing the same F waves. The source is staying still, producing the same F waves. The observer is going to move. Let's say he's going to move towards with the speed of VO. The observer is going to move with the speed of VO. What do you know about the wavelength? What's the wavelength here? Is it affected by, is this wavelength affected by the observer? Not at all. The wavelength is not affected, it's still V over F. So, what do you understand from here is, the observer's movement is not going to bother the wavelength. Wavelength is not affected. So now, let's find out what the observer is going to hear. The observer is going to hear a frequency F prime, which depends on two factors. One is the speed. Now, observer is moving this way. Which way is this wave moving? So these waves are hitting him at what speed?
F minus V up.
Say it again.
V minus V up.
Slower.
Faster.
Faster.
Oh yeah.
Relative.
V plus V up.
Imagine a car is not moving at all and you go and bump into him at 40 miles per hour. Compare that with the car is coming forward. The car is coming forward at 20 miles per hour and you go and bump into him at 40. What speed are you actually hitting him? 60. That's called relative velocity. You must have done that. Relative velocity. So what's happening here? The sound is moving that way at 340 meters per second. And if you're moving into the sound at 20 meters per second, it will appear as if the sound is moving at 360 meters per second. So it's higher. So this top part of it is V plus VO. It's a relative velocity. When someone is coming against you and you're going towards him, it's going to be adding up. That's the top part of it. The bottom part of it is a wavelength. What's the wavelength? V over F. Now that equation changes into F prime is equal to V plus VO over V and the whole thing times F. So what's going to happen? Will you hear a higher frequency or lower frequency? Higher. So right down here, observer moves towards source, stationary source. Observer moves towards stationary source. The frequency F prime is going to be higher than F. Okay? Now for the last one. The last one, the observer is going to go away. So if the observer is going to go away, so the observer is going to go this way at VO. Now, the frequency as heard by the observer is affected again by two factors. One is speed. With what speed are these hitting the observer? Yes, V minus VO. Now it is hitting slower because he is moving. Now what if the observer is moving at the speed of sound? It won't reach him at all. It's not going to reach him. You can just run away from sound. If you don't want to hear my lecture, you just run away from me at 340 meters per second. You won't hear me. Yeah.
What if we had like a source that was moving faster at the speed of sound? Would they get to the observer and then the observer would have to like wait for it to pass and then hear the sound?
Say that again. I couldn't follow.
Like you had a source.
Okay.
So I was flying a plane over your head.
Okay.
And I was going faster than the speed of sound.
Okay.
Would it like pass you and then you would hear the sound? Like after the plane was past you?
We'll come to the. I mean, so who's generating sound?
The plane.
The plane, and you're on the plane.
Yeah.
We'll talk about that. We're getting there.
Okay.
We're getting there. So I'll talk about that a little later. All right. So this is the speed with which the waves are coming to him. That speed over lambda. Lambda is not affected. So your final equation is F prime is V minus VO over V times F. And this is when the observer is moving away from the stationary source. So what's going to happen? Because the numerator has gone down, the frequency F prime is going to be smaller than F. You get it? So we saw four conditions. Source moving towards, source moving away, observer moving towards, observer moving away. We saw four of them. Yeah.
So, like, if the observer is moving away like the same speed as the waves, like he won't hear it.
No.
So
Yeah.
Like, I get like if it was going faster that he wouldn't hear it because the waves wouldn't catch up to him. But like if you're moving at the same speed as the waves, it's just like.
It's just like going parallel. So
It's like
Eventually the waves will, like when you stop.
yeah, if you are going to slow down and stop, then it will come and hit you back again.
Okay, but like what if you start out going slower and like you like accelerate and then are starting to go at the same speed as the waves?
Oh, then you'll hear for some time, and after that you'll just not hear after that. Yeah. What changes due to the source's movement? The wavelength changes. The speed doesn't change. What changes due to the observer's motion?
Speed.
The speed, not the wavelength. So basically, the numerator is going to be affected by the observer's motion, and the denominator is going to be affected by the source's motion, right? So we can just wind up the entire set of equations and the other thing you must have already noticed is this. If you look at all the four of them, you can see that when the source is moving towards the observer, frequency goes up. right? And when the observer is moving towards the source, frequency goes up. So the word towards means frequency goes up. The word away means frequency goes down. That makes it's easier then. So to put everything down into a one formula, here is your formula. V plus or minus VO, V plus or minus VS, the whole thing times F. That's one formula that you can use for Doppler effect. Just one formula. It contains everything. It contains everything. This formula you can use and solve any problem, but you need to choose plus or minus intelligently. You have to choose that plus or minus intelligently. Sometimes you can have both moving, sometimes you can have only one of them moving, right? If the observer is not moving at all, then take it out. If the source is not moving at all, then take this out. But if both are moving, you're going to have both of them, but you have to choose the signs now. How you choose the signs is this way. Towards F prime increases or goes up, right? Away, F prime should decrease. If anything is towards, frequency has to go up. This one has to go up. If anything is away, frequency has to go down. So let's look at it now. Right, so if the observer is going towards, what should happen to F prime because of the observer's motion? It should go up, right? Numerator has to go up, so you choose plus. So you will choose plus if the observer is going towards. You'll choose minus if the observer is going away. Now source. If the source is going towards, frequency should increase. And if the frequency has to increase, the denominator should decrease. And so you choose minus. That's why I said intelligently choose the signs. Yeah.
So you said if the source isn't moving or the observer isn't
Just
moving,
knock that out.
like the whole bottom.
No, only that part.
Okay.
Yeah, the other things will stay. If the source is not moving, remove this part. If the observer is not moving, remove that part. So this is the basic empirical relationship. You can just fiddle with that and come to any situation. Get it? Now let me give you some situations and then you just tell me what formula it is to be used. Here it is. Observer going this way. Source going this way. What equation are you going to use for this? Both are moving. So F prime is going to be V, VO, V, VS, F. Now the sign is the only matter here. Is the observer going towards? So what should happen to the top? Is the source going towards?
Yes.
So what should happen to the denominator?
Minus.
That's it. You got the equation. You understand that? How you choose the equation is just purely based on, you look at each one and say whether it's going towards or away. Yeah.
And they'll give us V and F. They'll give us all.
Yeah, you'll get enough variables. Yeah. Yeah, sure. Now, here's another situation. What's your equation there? Is the observer going towards?
This.
So you know what the top is. Is the source going? Is going away?
Yeah.
So what formula? What should happen to the frequency? Drop. If the frequency has to drop, the denominator should, and then times that. So you just kind of deduce those equations on the spot depending on what is happening. And a good idea is to draw these. According to the problem, you just draw the problem out, like which way they are moving, and then you'll know whether they're going towards or away. Get it? So the Doppler equation is not a tough thing to tackle. If you look at this equation and if you intelligently choose which one is plus or minus and all that, then it should be all right. I'll give one more. What is f prime? So, observer is going which way? So frequency should drop. If the frequency has to drop, what will you choose here? Now look at the source. Source is going away. Frequency should drop. If the frequency has to drop, what sign is going to be chosen here? Make sense? Yes? All right. What if the observer is going this way at 30 meters per second and the source is going that way at 30 meters per second? What's going to be the frequency?
Just regular.
Huh?
Just
The same as f. Correct. There's no difference. Because they're going together. So there's no relative velocity. You understand that? It's like in a train compartment. You're here, your friend is there, and the train is moving at a high speed. You don't have to worry about train. Your friend is moving away, and you're also moving. So both are going to same direction. So what happens is there's no relative velocity. It's like both of them not moving. Correct? These are both not moving. Only when the speed is different. Well, of course, if this is going to be moving this way, the story is entirely different. If he's moving this way at 30 meters per second, then the entire thing is different. So let me give you some number work now. Let's say a car. All right. A car sounds its horn at 1000 hertz and is moving that way at speed of 20 meters per second. And if another car, this is the observer. The observer is moving this way at 30 meters per second. And the speed of sound is 340 meters per second. Can you tell me what frequency is heard by the observer? What's the frequency as heard by the observer? The car is sounding the horn of 1000 hertz. And he's going that way. The observer is in another car moving this way at 30 meters per second. And what kind of frequency are you going to hear from that? So first thing, set up the equation. Then start substituting. So that's a source. Anything that's emitting the sound is a source. So first set up the equation. You got it? How much is it?
I got 1,156.25.
Well, he says 1,156. Is that right? Okay, looks right then. Okay, let's see how it works. Source is going, observer. It's always good to tackle the observer first because that's the numerator. Okay? To not get confused, tackle the observer first. Observer is moving towards, which means frequency tends to increase, therefore you put plus. Source is moving towards, that means frequency again tends to increase, so the bottom has to go down. And then times that. That's what you should do. So 340 plus 30 divided by 340 minus 20 times 1000. So what is it? 1,153?
46.
So you tend to hear a higher pitch than what actually is being emitted. This is something that we normally hear. Normally hear this. Yeah.
So if you're going over 340 meters per second at a wave, then that's the point when you won't be able to hear it.
This way or that way?
If you're the observer and you're moving away, you move.
If you're moving away, that's when there's jets. Now, if you've seen a race car, if you are the audience, if you're sitting there and watching the race car coming from there, you are a stationary observer. You're not moving. So because you're a stationary observer, this part is gone. It's just V. Now the car engine has a frequency, right? Because when the car is coming from there, there is a car engine frequency. It's not pressing the horn, but there's an engine frequency. That sort of frequency. The engine frequency, like your RPM. The RPM comes there. So when the car is accelerating from there and coming on fast, the RPM of the engine creates that frequency. So you are hearing the engine frequency. Are you hearing a higher pitch or lower pitch when the car is approaching you? Higher. And as soon as it goes by you, it becomes lower because now he's going away. He's coming towards, you have a higher frequency. When he goes away, suddenly the frequency kind of drops. Suddenly drops. It's up to here, it will be like, right, exactly. Yeah, sudden drop. It's like, just sudden drop. Get it? So that is completely Doppler effect. The engine frequency stays exactly the same. But why the frequency changes right in front of you is because till then he was approaching you. And all of a sudden he's now going away from you. So the entire thing is different. Yeah.
Is there any point like that you can't hear it because like if you're so far away?
How you're able to say if an ambulance is coming towards you or away from you is just by listening to the pitch. If you are in one car and if an ambulance is approaching you, you can actually figure it out. If an ambulance is going away from you, that will be clearly audible because the pitch is different. So the Doppler effect is something that is commonly seen. Now cops find your speed by using Doppler effect. How fast your car is moving is also found by Doppler effect. Now what happens if you are traveling, if you are in a plane creating waves? So this is the plane and you're creating waves in the plane. So the waves are going forward and backward. Waves are going. So when the waves are going in one direction and if you are also moving in that same direction, then the waves are going to be created like that. The waves are going to be created like this. It's crowding at one spot here. These are all crowded. And your plane is moving that way. But what happens is, well, what is this? What are these lines? Compressions. Those are compressions that are traveling. So as you're trying to approach that part, those compressions, they get closer and closer and closer. Depending upon your speed, the compressions are getting closer and closer. It comes to a point that it actually kind of forms a wall of compression. It's just a wall like this. When they all kind of merge together at one spot, all those sounds were produced. They produce so many compressions, and all of them are really compressed to one wall. One solid wall of compression. And now if you travel faster than that speed of sound, then what happens is you are creating that wall in front of you and you're breaking that wall also. So when you break that wall, the plane is kind of tearing through that wall. So think of this. Imagine a wall, a compression wall, and you just pass through it. When you pass through it, you're just tearing it open momentarily. As soon as you cross, what happens? There is a kind of void because of you just left. And because of the void, the compressed air is going to come in. And when it comes in, it creates high pressure once again. And the high pressure, along with all the, so the high pressure actually kind of forms condensations and stuff like that too. As soon as that happens, you can see it creates a kind of misty appearance behind the sonic boom appearance, like, kind of a tail, right? That is produced because of this concept. Because when a supersonic jet is flying at a speed more than speed of sound, it is tearing its own compression wall, and so as it tears the compression wall, the compression is coming back. The sound, it's coming back, and when it comes back like thunder. Thunder. What is thunder? Thunder is again coming back. This is thunder. When lightning is formed, what happens when lightning is formed? It produces so much heat, so there will be an expansion. The air expands, and it expands and creates a void. And when that void is created, as soon as the void is created, the air that went away from there comes back and hits. And that is what we call as thunder. And this is, when a plane goes faster than the speed of sound, it's going to cause continuous thundering sounds. And that's why it's kind of pretty loud. That is pretty loud. So when air gets back in, it causes sound. Just something like this. Where's the sound coming from? The sound, where is it coming from? My tongue is soft tissue. Inside my linings are also soft. Everything's soft. It's not like a solid object hitting a solid object. Tongue hitting or tongue in contact with. So both are kind of soft tissues. How is the sound coming from? Where's the sound coming from? The sound is coming because when I put my tongue there and then pulled my tongue, all of a sudden, it created a void. And as soon as it created a void, air is rushing back in. And that creates that sudden compression. And that's what is same as your clap. Your hand is soft. This hand is soft. But the sound that comes up is really high. Yes?
Is that what happens whenever you break the speed of light? Also, it's kind of like the same.
Break the speed up?
What?
Yeah, if you were able to break the speed of light, if you're able to go with that. If you could use that, we should already
No one